on, yeah? The reverse of it would be this. Sound and heat from the bullet start making the lead vibrate. A perfectly formed lead bullet is formed from spatters of lead and molten lead, and a deformed bullet. The bullet is reshaped by the vibrations of the wood. The fibers of the wood are miraculously reconnected, right? And all that heat energy, the block gets colder and the bullet gets colder, and all that random motion of the molecules in a concerted effort fling the bullet back out of the block at a greater velocity. Yes? And the block is unscathed after this, yes? I think we're seeing it backwards, aren't we? We know, yeah, this has to do with like entropy and all this stuff, right? Okay, so elastic collisions are reversible. Inelastic collisions are sticky, so let's see an inelastic collision. Here's one. And we're going to do a momentum lab. You'll get to use these air tracks, and you'll do a momentum lab, and we will try to determine whether momentum is conserved, which we probably think it is, right? But here is an inelastic collision. Watch, they hit and they stopped dead. Did you see that? They stopped moving. I got the velocity just perfect. If you weren't paying attention, you might know. You might think that I did that, right? Okay, I got the velocity so perfect because I'm just like a freaking human calculator, right? Okay, and I gave that thing exactly the right push, so when they collided, they stopped absolutely dead. Now, before the collision, you have kinetic energy. Afterwards, you have? Heat. Yeah, heat or something, but you don't have kinetic energy, correct? Of these things, right? Momentum is conserved, no problem there. We had positive and negative momentums in equal amount, and afterwards we had, well, still a sum of zero momentum, right? But energy-wise, the energy all went away, right? Okay, so that when we say that they're sticky and crumply and stuff like this, that's what we're talking about. Kinetic energy is not conserved. In fact, in this case, this is the extreme example. That is a perfectly inelastic collision, right? It is not conserved at all. There's none left. It's all gone. It's all gone. Hello, you have cookies?
Yes.
Yes, please.
Cents.
How much?
25 cents. 25
cents for a cookie. That is the best deal. How much are they at Starbucks? 10 times that.
150.
No, no. I just said it's 10 times. I said it's $2.50. Checks payable to what?
Emily.
Okay, yeah. There you go. Are you Emily Ben Jumbo?
Yeah, I am.
Are you going to take physics?
No, I'm a senior.
Physics was your sister's favorite course.
I know, she told me.
Really? Was it really? I was just making that up.
She loves you.
Yeah, I love her.
Okay, good.
I could have loved you. No, I'm just teasing. I'm teasing. I do love you.
Okay, good.
Not in a weird way. All right. Am I recording? Oh, okay. Yeah, she's gone. That got rid of her, didn't it? Here we go. Okay. Okay, so the bullet in the wood, I'm blushing. Okay. The bullet in the wood is inelastic, right? We've showed that the energy was not conserved, right? And then a car bumper, if your car bumper hits something at a velocity greater than 5 miles per hour, okay? Something you have to tell your parents about that one, don't you? Yeah, right? So car bumpers below 5 miles an hour, they protect you. They've got an elasticity in them. They bounce, right? Okay. Above 5 miles an hour, your car is strategically designed to be not elastic. Have you ever heard these stories of somebody say, well, gee, I didn't hit him that hard, but it caused $3,000 worth of damage? Yes? Have you heard that? Yes, that's because your car is designed to be not strong. Your car is designed to be not strong. It's designed to crumple strategically. Yeah? Okay. So, and then this is the basic idea. Back in the day, okay, they would make cars out of extremely strong things, and then they would wonder why people didn't survive car crashes. Okay, like for example, nowadays they actually design cars actually to be not as strong as they could be, right? In certain areas, like outside of the thing protecting the drivers. An example of this is when I looked at the frame parts of my Volkswagen Rabbit, right? The first car I owned, second car I owned, right? Okay, the frame part, instead of being a piece of steel tubing, instead of being a dead pen, what is wrong with this pen? That's sad. Okay, instead of being a perfect tube, well, perfect tubes are amazingly strong. You can take a straw, if you plug the end of it, stuff it through a potato. Yeah? This is one of these tricks that they do. They'll probably do it at the physics extravaganza. It's a perennial favorite, right? Okay. They could have made that thing connecting the firewall of the car to the bumper out of tubing, and it would have been really, really strong. I could have plowed through buildings with that thing. But instead, they actually made it out of like a piece that they had They put like little things in it like this, yeah? It's so hard to draw. Yeah? It was like pre-accordion. It was like one of those crinkly straws, those bendy straws, all straightened out. Yeah? What's this going to do when it hits something solid? It's going to crush, isn't it? Isn't it going to absorb a lot of energy doing that, though? Yeah. That's the idea, yeah? So you want to actually absorb the energy in the impact, right? So here's how you keep drivers safe, right? Besides educating them and all this stuff, right? Okay. What you do is you make the part of the car around the driver, the frame right around the driver, the cage, as it were, and the sidebars and the side panels, you want to make that as strong and as rigid as possible. Right? People can survive 70-mile-an-hour collisions with a brick wall in a smart car because the shape of that thing, look at that, it's like egg-shaped, right? Inside that space, you want to restrain the driver. That's what your seatbelts have, right? In fact, your seatbelts even have, not only do they lock on impact, they've got things called pre-tensioners, right? They're little things, little gizmos, I don't know how they work, that pull you back into your seat and tighten your seatbelt and lock it, right? So if you were like reaching forward, it goes, oh no you don't, bam, back you are in the seat, right? With your head against the headrest, that's why you got to adjust the headrest just right. And then they inflate using explosives, this big bouncy bag right in front of you. Yeah? So you're surrounded by this rigid thing that keeps like car bumpers and things from intruding in there. You're pinned against your seat with this big inflated bag. Everything outside of the car is designed to be weak, not so weak that it just crumples immediately, but weak enough that it absorbs most foreseeable impacts, right? So they could make cars so they would just have like very little damage at high-speed collisions, but then you die, right? You know, and so and by the way, the automobile industry, they didn't do this like the automobile industry didn't do this out of some altruistic thing like we must save lives, because that really doesn't sell cars, right? When seatbelts were shown to save lives in experimental tests, right? The auto industry fought it tooth and nail and had to be forced by using laws, right, to do it, right? And when airbags were shown to save lives, right? The auto industry said, oh, nobody wants this. They fought it tooth and nail, right? And they had to be forced using laws to actually put these things in there. Why is that? Is that because airbags add like $1,500 to the price of a car? And this is a free market society, and so if you make a car cheaper than somebody else, and it's got this thing that might explode on you, and you're paying $1,500, I'd be like, no, I don't want to buy that, right? People aren't even interested in their own safety, right? So this is why government has to do that, right? Because otherwise we wouldn't do it for ourselves. I don't know. Something like that. I think that's a good thing. Is that a good thing? I think it's a good thing that fewer people die. Isn't it? I think so. Yeah, I don't know. Depends on your definition of good and bad. And then we've already talked about inelastic collisions are irreversible. I think it's time to demonstrate some things. So I don't think we need this. Power off. Yes. I've got my list of demonstrations. Okay, my very first demonstration is this. Don't text. All right. All right. Here is, and I'm really going to have to ask you guys in this case, I'm not going to have you sign the form and everything, like I will not disclose the secrets or whatever, but this is something I've invented that I really appreciate you not telling my competitors. You just don't be vague about some of the details, okay? But here is the notion, is that in theory, if you understand that all matter is made of atoms, and atoms are mostly, what are atoms mostly by volume? By volume, atoms are mostly empty space. Atoms are mostly nothing. Isn't that crazy? Okay? And so if we were to make an atom the size of the Rose Garden Arena, picture that. That is one big ass atom, right? Okay, right? Okay. And if we were to do that, almost all of its mass would be a little thing about the size of a golf ball or a grape or something, depending on what kind of element you have, right? In the center of the Rose Garden Arena, yes? The thing that defines the extent of the atom are these little electrons buzzing around, yes? Sort of like the blades of a fan, right? They don't occupy all that space, but you can't put your finger in there, right? They hit you. Or like one of those little yappy dogs inside a fence, right? It's like yap, 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 yap. It's not everywhere inside that yard, but it prevents you from entering the yard effectively, doesn't it? Yeah, there we go, right? Okay, so that's the model of an atom. And so in theory, shouldn't I be able to pass one solid object through another And those nuclei they wouldn't even touch each other. And if they got near each other, they'd repel each other. And shouldn't they all be able to kind of just